This is the fifth lecture of the course MTH 204A for section B. In this lecture, we will talk about group actions. Let G be a group and X be a non-empty set. We say that G acts on X by symmetries. G acts on X by symmetries if, informally speaking, every group element G gives rise to a symmetry sigma G of X. Let me again remind you that here by symmetry we mean a bijective mapping from X to X. So we say G acts on X by symmetries, or simply G acts on X if every group element G yields a symmetry sigma G of X in a coherent manner. So what I mean by this is this assignment G goes to sigma G for any G in G. This assignment preserves the group laws. So what I mean by this is, so here this assignment is actually a map from G to Sx, and we want this map to preserve the structures of the groups. So to put it in the formal way, we say that G acts on X by symmetries if there is a group homomorphism from G to Sx. I repeat that the situation is we have a group and a non-empty set. So every element from the group is giving a symmetry of the set under consideration in a coherent manner. That is why you are calling it the group acts on the set by symmetries, because every group element is, again, intuitively speaking, every group element is actually acting on the set by symmetries. Every group element is giving a symmetry of the set, and since both G and Sx, they are groups, so this assignment G to Sx is we insist that it preserves the structures. So it's a map that preserves the structures of the groups. So which is exactly meant by saying this is a homomorphism. All right. So given an action that is a homomorphism from G to Sx, given an action for any group element G and X, we consider the sigma G applied on X. This has to be a point in X. So this motivates us to consider the following function from G cross X to X. So how this function is defined? So for any pair G comma X, we send that pair to the point sigma G of X. So this is a function from G cross X to X, and since sigma is a homomorphism, since sigma preserves the structures of the groups, from this it's easy to see that the function alpha we have just defined satisfies these two properties. So whenever we are given a homomorphism sigma from G to Sx, from that we can construct a map from G cross X to X, a map alpha from G cross X to X satisfying these two properties. Now let's look at the reverse situation. That is, now suppose we are given a map alpha from G cross X to X with these two properties. Suppose that is now given to us. Then we see that we can indeed define a homomorphism sigma from G to Sx in the following manner. So for each group element G, we define the map sigma G. So the sigma G is defined in this way that for each X, sigma G sends X to alpha of Gx. So it is a routine verification that sigma G defined in this manner is indeed a 1:1 map from X to X. That's actually clear because you can immediately verify using these two properties that the inverse of this map sigma G is sigma G inverse, sigma of G inverse. Okay. So thus we see that sigma g is indeed a symmetry of the set X. Furthermore, again from these two properties, we can easily show that this assignment G goes to sigma G, this assignment G goes to sigma G is indeed a homomorphism. So thus what we have seen is the following, that given a homomorphism sigma from G to Sx, we can construct a map alpha from G cross X to X with two properties listed here. Conversely, if we are given an alpha, a map from G cross X to X with these two properties, then from that we can construct a homomorphism. We can construct a homomorphism sigma from G to Sx. So again, let me repeat that we have a mechanism to construct alpha from a given sigma, and we also do have another mechanism to construct a sigma from a given alpha. Now I leave this to you to check that these two mechanisms are indeed inverse to each other. That is when we are given a sigma, from that we construct the corresponding alpha in this manner, and then from that alpha, when we construct the homomorphism, then we will get sigma back. Okay, so from sigma we go to alpha, then from the alpha, when we will construct the homomorphism in this manner, we see that we are getting our sigma back. So similarly for the other one as well. So thus it follows that this correspondence between sigma and this correspondence between sigma and alpha indeed establishes a bijective this correspondence sigma to alpha is indeed gives us a bijective mapping between these two sets. So in the first, in the left, we have the collection of all homomorphisms from G to Sx, and on this on the right we have the collection of all functions from G cross X to X with these two properties. So in one hand I have the collections of sigmas, and on the other hand we have the collections of alphas, and we have just discussed that we can establish a bijective correspondence between these two collections. So in view of this correspondence, we can alternatively define an action as a map from G cross X to X satisfying these two properties. So let me repeat. So though we have started the definition of the action of a group using by a homomorphism from G to Sx, then later on we observed that that's exactly same as saying having a map from G cross X to X with these two properties. So in view of this equivalence, we can alternatively define an action to be a map from G cross X to X satisfying these two properties. In fact, in most of the standard textbooks, the action is defined by this, and later on you will see that there are certain advantages. In defining actions as a map like this. There are certain advantages compared to define by this. However, as we have seen that these two are equivalent, so there should not be any problem in that. And in our discussion, we will use both according to our convenience. So what I mean by that, when it is convenient to express in terms of homomorphism, we will define action by this, and also when this one will be more convenient. So when define an action when this one will be more convenient, we will use that. So in view of this bijective correspondence, again it is we can use either of them according to our choice. Okay, But however, let me again telling you that defining action in this way, by action by a function like this, has certain advantages which you will see later on. All right. So okay, so let me set the notation. So if if this is my map, so if this is my action map, then we denote this by G, this curved right arrow, and on the top I mention the map. So the reason for mentioning this map is quite obvious, that for the same G and X we will see examples. So for the same G and X, there could be several alphas with the desired two properties. So what I mean by that is the same group can act on the same set in different ways. So therefore, to distinguish them, we should mention the action map on in the notation. But however, in order to simplify the notations, when there is no danger of confusion, we may drop alpha from the notation. And also furthermore, we once we drop alpha, then we once we drop alpha from the notation, then this in place of this we simply write this. Okay. So as I said, that in order to simplify the notations, we drop, when there is no danger of confusion, we drop alpha from the notation and simply write gx in the place of alpha of gx for any g and x. So after this simplification, we see that these two conditions look like this. So alpha 1x is simply 1x is x for every x, and the second condition now looks like g1 g2x is g1 of g2x. So now they look really simple after simplifying the notations like here. Now these two conditions look really simple and natural. All right. And as I said that in most of the textbooks, group actions are defined in this manner. For us, we will use either of them depending upon the situation. But however, since the standard way of defining an action is by this, so the corresponding homomorphism is called the permutation presentation of the action. So here you see that our approach was somewhat our approach was the opposite to the standard one, opposite to the approach adopted by the standard textbooks. That is, we started with this homomorphism, and from that we get the alpha, and then of course we proved their equivalence. Okay. So now what we will see is something very interesting, that if a group acts on a set X, then that naturally acts on the space of all functions. So given a set X, we denote Lx is to be the set of all functions from X to C. Here C is not serious. You can take R or Q, whatever you wish. But in order to, there will be situations where several equations will come up whose roots we will need. So, but if the field is real, then those equations, those polynomials may not have any roots. So to avoid all such unpleasant situations, we consider C instead of F or R. But whatever I am going to talk about, mostly it goes for a Q or R, or in fact over any general field. Okay. So the reason for considering C is that it's algebraically closed and nothing else. Anyway, so given X, we consider the function space. This is the space of all functions from X to C. It's a complex vector space. And for any G and F, we define GF to be the function by this. So by this, and it's a routine verification that this indeed defines an action of G on G on Lx. Here let me tell you that if instead of G inverse, if you just take f of gx, if you define G of f of x to be like this, then it is not going to be an action. So I leave this. I leave this verification to you. So because if you define it by this, then at some point of time the G1 and G2, their orders will be flipped. So in order to take care of this, we take G inverse from the beginning. Okay. Having verified that it defines an action of G on Lx, we observe that for any G, the map which sends the map from Lx to Lx, which sends each F to GF, is actually linear. So, I mean, here what we have obtained is each group element. So So first we obtain that given an action of G on X, then the G has a natural action on the space of functions. So thus every group element G is giving a symmetry of the vector space, is giving a symmetry of Lx. And now in addition, since Lx is a very complex vector space, in addition to being just a bijective map, we can also see that the f goes to gf is linear. So thus, in putting things together, what we obtain is every group element is giving us a symmetry of the vector space V, that is a linear automorphism of the vector space. Okay. Since these are linear automorphisms, so the permutation presentation, since these are linear automorphisms, since for each G this is a linear automorphisms, therefore we indeed get a homomorphism from G to GL of Lx. So let me again repeat that G acts on Lx, and corresponding to every group element G, the symmetry that we obtain is in fact a linear symmetry, that is a linear automorphism. Therefore, if we now look at the permutation presentation of this action of G on Lx, we in fact get a homomorphism from G to GL of Lx, because corresponding to every small group element G, the symmetry that we are getting is in fact lies inside the general linear group of this vector space Lx. Okay. So given an action of G given action of a group G on a set X, we obtain a homomorphism from G to the general linear group of the function space over X. A homomorphism. This homomorphism is called the permutation representation associated with the action of G on X. I repeat, so given an action of G on X, we obtain an action of G on Lx. Then if we look at the permutation presentation of the later, then we see that we in fact get a homomorphism from G to the general linear group of the vector space Lx. So given the action of G on X, this homomorphism is called the permutation representation associated with the action of G on X. The reason for calling this representation will be clear soon. Okay. Now let's move on. So for any x in X, let Ex denotes the map which takes the value 1 at the point X and 0 elsewhere. And it's easy to see that if G, for any group element G and X in X, if the group element G acts on Ex, then it yields E of Gx. That's clear from the definition. Okay. So for this functions, when we apply, if we want to see that where a group element sends these functions, we see that a typical function Ex will be moved to E of Gx by the group element G. When x is finite, then this ex's form a basis of the function space. That is, I presume that you must have done in your linear algebra course. So since this is going to be a basis of Lx, and then every function f in Lx should be a linear combination of these ex's, and in fact it's easy to see that each f is nothing but if for each f is nothing is exactly this linear combination of ex's. Okay, so the scalars here will be exactly values of values of f at the point x, and now it's from this it follows immediately that g of f is nothing but since f is the sum, and since applying G is a linear map which we have just seen, so G of f will be summation fx into G of Ex, summation fx into G applied on Ex, and that gives us this. So now I would like to leave the following exercise to you, that if x is finite, then for any group element G, the linear group element G, what is going to be the trace of this linear map. Let me again repeat. So we have observed that irrespective of x finite or not, we have observed that for each G, f goes to Gf is a linear map from Lx to Lx. Now in the case of x is finite, then Lx is going to be a finite dimensional vector space over C, and in this exercise you have been asked to find out the trace of this linear map. Okay, so I would like to make the following remarks here, which are also quite important. So given an action of G on X, if H is a subgroup of G, then H also has a natural action on X, and the permutation presentation and representation as well of this action are restrictions of those of the given action of G to H respectively. So let me explain what I mean. That recall that permutation presentation. So as I said that following the standard approach, we will be mostly defining actions by this. So if we define the action like by this, then the corresponding sigma is called the permutation presentation corresponding to that action, and the permutation representation is the homomorphism from G to the general linear group of Lx. So given an action of G on X, if we consider a subgroup H of G, then H has a natural action on X, namely in the exactly similar manner in which G acts on X, and the permutation presentation and representation as well of this action of H is nothing but the restrictions of the permutation presentation and the representation of G, permutation presentation and representation of the original action of G respectively. Okay, so this is one thing which is quite easy to see. And the second remark that I want to make is the notion of action can be extended to semi-groups. So here we defined the notion of when a group G acts on a set by symmetries. We define the notion of an action of a group. So this remark, in this remark, I would like to say that the notion of this action can be extended to semigroups. So what is a semigroup? A semigroup is just algebraic structure which is just one step before being a group. That is, it's associative, having an identity, but it may not admit inverse. Okay, but it may, yeah. So it's a binary structure, associative, having an identity, but all the elements may not admit their inverses. Just one step behind the group. Okay, so if G is a semigroup, when we say G acts on X, we mean that. So we have similar to what we have seen for group actions of groups, we have a map from G cross X to X with these two properties. So the here also, and so let me again explain. So as I say, if we define, if you note that, if you observe that the way the action is defined as a map from G cross X to X satisfying these two properties, you see that in order to be mathematically meaningful for these two properties, we don't need the elements G, all the elements G, or in fact any element G has to have an inverse, that we don't need. Okay, so even if G doesn't, even if G does, this G1 and G2 do not have inverses, still these two properties, still the properties make sense. So therefore we see that we can extend the notion of action to semigroups as well. That is some map from G cross X to X with these two properties. Okay, or equivalently, we have a map from we have a homomorphism. Well, here it's not technically correct to say homomorphisms, rather we should say the structure preserving map from G to fx, the G to the all functions from collection of all functions from X to X, which is easily seen to form a semigroup with respect to composition. So this is a semigroup, this is a semigroup. So the map insists that it preserves the structure. That is sigma of G1, G2 is the composition of sigma G1 and sigma G2. So defining an action of a semigroup as a map with these two properties is equivalent to saying that having a structure preserving map from this semigroup to this, from this semigroup to that semigroup. Okay, and and the difference here from the previous situation is that here sigma g's may not be bijective. Okay, here the sigma g's that may not be bijective if G is not a group. All right, so when we are it is customary to call the actions of R, or the set of, or the action of the semigroup of the all semigroup of all non-negative real numbers. It's customary to call the actions of R or non-negative real numbers, call them flows. I repeat, so by a flow we just mean is when we say that we are having a flow, it means that it means that R or the semigroup of all non-negative reals is acting. Then we some often call those actions as flows. Yeah, we often call those actions. We call those actions flows. Okay, so a flow is nothing but an action of the group of reals or the semigroup of all non-negative reals. Let me make it very clear. I think that clarifies everything. Okay, let's go ahead. Now, before we look at some examples, I would like to leave the following exercise to you. So what it says is, the first exercise says that if G has an action on X and a subset of X, Y, say Y is G invariant, that is for every Y in Y and G in G, the GY is in Y. So if you have an action and Y is a G invariant subset of X, then you see that G acts on Y naturally. The second exercise says that given a non-empty finite set having an action of a group G, then for any k between any positive integer k not exceeding the number of elements of X, if we consider the collection of all subsets, all k subsets of X, then there is a natural action of G on this collection, because since each group element G is giving a bijection, right? So therefore, having a case, if we are having a set of k elements, then its direct image under the bijection given by G, it will also be a set with exactly k elements. Okay. The third one says that suppose we are given a finite collection of sets x1 up to xk, non-empty sets, and G has an action on each of these xi's, then from this we can construct an action, a natural action of G on the Cartesian product of these sets. So how do we define such an action? So basically, you see, basically it is just component wise. Okay. So now we will see examples. So we will see a lot of examples, in fact, of group actions. So not only the rest of this lecture, the next lecture will also discuss many other examples. So basically, you see that one full lecture and perhaps more than half of this lecture we will for such a long period, for quite some time, we will be discussing several examples. The reason for that is that though we are studying group actions in the algebra course, but this is nothing specific to algebra, that the actions happen everywhere in mathematics. So we must see diverse examples. We must see examples from various areas of mathematics, I should say. Anyway, so let's start. So the first example is a natural one. Because why this is natural? Because in the beginning we say that a group acts on a set X. By that, what we mean is every group element is giving a symmetry of the set X. Okay. So in view of that, our first example is for any given non-empty set X, the action of its symmetric group of X on X. Okay. So given a non-empty finite set X, its symmetric group acts on X in the most natural way. As a special case of this, we see that for every maybe instead of writing this for all n greater or equal to n, maybe we can simply, because when n equal to 1 or 2, those cases are not at all that much of an interest. So yeah. For Sn acts, so yeah, as a special case we obtain that Sn acts on the set 1 up to n. So what's the permutation presentation of this action? This is simply the identity map, because the symmetry, because when X is this, then Sx will be Sn. So the permutation presentation of this action will be. So in fact, I mean, that goes even here, that for any x, for any set x, for this natural action, the permutation presentation is the identity map. Okay, and the yeah, so the permutation presentation is trivially seen to be the identity map. We now look at the permutation representation in this special case. So what's the permutation representation for this action? So the permutation representation is the homomorphism that sends each element sigma of Sn to the following linear transformation. So what's the linear transformation? So given a tuple x1 up to xn, the linear so the linear transformation sends this tuple x1 up to xn to this tuple. So you see that it is just permuting the coordinates of this tuple. So so this is the permutation representation associated with this action. And so this is a map from Sn to, so this is a map from Sn to the GL of Cn. Okay, now remember that GL of Cn and GL and C are isomorphic. So if we compose this permutation representation with this isomorphism, we obtain the following, just a minute, so we obtain the following homomorphism from Sn to GL and C that sends each sigma to this matrix. So it's nothing surprising, because for any given sigma, what's the matrix of this linear operator T sigma? This is precisely this. So thus we obtain a homomorphism from Sn to the general linear group, and it's clear that the above homomorphism is injective, and as a result of this, we see that Sn is isomorphic to a subgroup of GL and C, namely the subgroup of all permutation matrices. Okay. The next special case of this is the following, which is basically from analysis. So here we consider X to be the set of all natural numbers. So of course, as Sn, the symmetry group of n acts on n, so from that action we get an action of Sn on Ln. So what is Ln? Is the set of all functions from n to c. In our usual terms, Ln is nothing but like a function from n to c. What do we call it? We call it a sequence, a complex sequence, right? So here, from the action of Sn upon Sn on n, we get an action of Sn on the space of all complex sequences. So at this point, I would like to leave this to you to check that under this action, these sets are invariant, and hence the Sn has a natural action on these sets. So the first set is the set of all convergent sequences. So saying that this is invariant under the action of Sn is equivalent to say that if a sequence is convergent, then under any rearrangement of its terms, it will be convergent as well. And the second collection, this is in fact like for each P we have a collection, and which is basically the collection of all sequences which satisfies this. So this space is called little LP. So it's for example, if P is equal to 1, then little L1 is nothing but the sequences such that the corresponding series is absolutely summable. Okay. Now let's move on to the next example. The next example is about the actions of these important subgroups of Sn, namely alternating groups, dihedral groups. So since Sn acts on this set, automatically n, d2n, all those sets, I mean, and other such subgroups of Sn will automatically act on this set 1 up to n. Geometrically, so this for d to n, the action of d to n on 1 up to n can be perceived geometrically as follows. Remember that d to n is nothing but group of symmetries of a regular polygon Pn. So the action of d to n on 1 up to n can be geometrically perceived as the action of the symmetric group of Pn on the vertices, or on the set of vertices of Pn. So like a symmetry of a regular polygon Pn, what it does is it permutes the vertices and permutes the, of course, edges as well, right? So from that we can visualize this action, this purely algebraic, this action written purely algebraically. We can perceive this purely algebraic action in geometrically like this. Okay. For any n greater or equal to 3, consider all these sets consisting. So let me simply write what we have here. So yeah. So maybe better to put better to depict that. So for each I from 1 up to n, we take I to I plus 1 and I to I plus 1, this set, and together having all such things collected. With that, we would like to add one more thing. So there's a small mistake while writing. Yes, it will be the 1n. Okay. So this is our collection. So so in this collection we have all such sets, all such 2-element sets together with this 1n. So you might wonder why we are considering such such a set. That's exactly because if we now think of the picture of the regular polygon with vertices labeled, then you see that each of these basically corresponds to a edge, corresponds to the side of that regular polygon. So thus the action of dn on this set En can be perceived as the action of dn on the sides of the regular polygon Pn. So this is quite natural, because it's d2n is nothing but the group of symmetries of Pn. Okay, now let's move on to the next action. So the next action is due by the linear groups of any vector space. So given a vector space V, it's the group of all invertible linear operators acts on this vector space in this natural way. In particular, where if in fact for any n, we obtain that GLNF acts on Fn, and since GLNF acts on Fn, then SLNF and of course the subgroup of all scalar subgroup of all scalar matrices where the scalar is non-zero, because things are diagonal in things, because the matrix has to be invertible. So this subgroup of GLNF, which is in fact isomorphic to the multiplicative group of the field, also acts on Fn. In the special case, when in the case when F is R, we further we further have natural actions of the orthogonal group or special orthogonal group on Rn. Okay. Yeah. And in case of F equal to C, we obtain further, we obtain actions of these important groups, namely the unitary groups, special unitary groups on Cn. Okay, so basically all these are originating from the action of the general linear group on the vector space. So since for any field f, GLNF acts on Fn, so any subgroup of GLNF, namely SLNF, will also act on Fn. And when F is R, we have some more interesting subgroups, namely this orthogonal groups, special orthogonal groups. They will also act on Rn. Similarly, the complex case. All right. And the permutation representation of the action of GLV, remember that the GLV acts on V in this manner. So it's easy to see that the permutation representation of this permutation representation associated to this action is nothing but the identity automorphism of the group GLV. Okay, so what we have seen is, we have first seen the action of the symmetric group of a given set on that set itself. The next example with what we see, broadly the next, if we divide things into broad categories, the next category of example that we have seen is the action of the general linear groups of a vector space on that vector space. The action of the general linear group of a given vector space on the vector space itself. Now assume that V is finite dimensional and let R be a natural number not exceeding the dimension V. So now we consider the set of all collections of R dimensional subspaces of V, which we denote by GRV. So since given a R dimensional subspace of V, if we consider its image under a linear map, it is again going to be a subspace of the same dimension as A is an invertible linear map. So that shows that there we do have a natural action of GLV on this set as well. So as a special case, when small r equal to 1, we obtain a small r equal to 1 and as a special, and V equal to V equal to Fn, we obtain the action of GLN. Just a minute. So as a special case of this, when V equal to Fn plus 1, when V equal to Fn plus 1, we obtain the action of GLN plus 1F on this projective n space over F. So what is this? This is nothing but the collection of all one-dimensional subspaces of Fn plus 1. So this is called the projective n space over F. So for each n, we obtain the action of GLN plus 1F on the projective n space over F. And similarly, once GLN acts, we do have the action of SLN plus 1 as well. Before we go ahead, I would like to leave the following exercises to you. Given an action of G on a set X, and if sigma is its permutation representation, then any normal subgroup N, normal subgroup of G, any normal subgroup N of G any normal subgroup N of G which is contained inside the kernel of this permutation representation sigma, for any such normal subgroup N, we obtain a natural action of G mod N on the set X. That's quite clear because since N is a normal subgroup contained in the kernel, so automatically we do have a homomorphism from G mod N to Sx. Okay. So given an action, from that we can, given an action of G on X, from that we can construct actions of the factor groups, actions of the factor groups on the same set X, such that actions of those factor groups on the same set X, for which the corresponding normal subgroup is contained inside the kernel. So as a particular case of this, we see that for any n, so this projective general linear group. So what is a projective general linear group? This is nothing but GLNF modulo the space modulo the all invertible subgroup of all invertible scalar matrices that acts on this projective n space. Similarly, we do have the action of projective special linear group. So this is nothing but this all scalar matrices whose determinant is 1. So for example, when n is 1, PSL2R is nothing but SL2R factor plus minus I2. Okay. This is because that in the first case this group, and in the second case this group is actually contained in the kernel of the permutation presentation of that action. That's quite easy to see. I leave all these verifications to you as usual. Okay. So let me make a remark here. So for any action of G on X, we define its kernel to be the kernel of the permutation presentation sigma. If the kernel is trivial, we say that the action is faithful. For example, for the action of Sx on X, it is going to be faithful, and similarly the above mentioned actions of projective general linear group and projective special linear group are also faithful. I leave the routine verifications to you. Okay, let's move on to the fourth example. As I said already that we will see varieties of examples. We will see a diverse class of examples from several topics and maybe from several branches of mathematics. So the next example of actions that we are going to see is related to differential equations. To be more precise, to be more specific, ordinary autonomous differential equations, so which we also say as initial value problems. So let n be a natural number and let f be a continuously differentiable function from Rn to R. For each x in Rn, we consider the following initial value problem. So assume that for every x in Rn, this IVP has a unique solution. What I mean by this is there's a unique curve, C1 curve from R to Rn satisfying this two conditions. Okay. So let me here tell you that it is not the case that for NEF you will have it is not the case that for NEF a solution will always exist, and even if the solution exists, there is no guarantee that this solution will be defined over the whole R. When f satisfies Lipschitz condition, which is automatically guaranteed when f is C1, then Picard's theorem guarantees the existence of solutions locally. So let me again try to explain that it's not guaranteed that you will always have solutions for NEF. So Picard's theorem gives us the existence under certain hypothesis on f, but that's also local. That is, in some neighborhood of 0 there will be a solution. Of course, the Picard's on that neighborhood, Picard's theorem guarantees the uniqueness of the solution as well. But let's not get into all this analytic stuff here. Instead, we are considering those f only for which there is a unique global solution corresponding to any initial point. I repeat that this for any x having the existence and uniqueness of solution is not guaranteed. uh, by means of Picard's theorem, we can talk about existence and uniqueness locally, but however, let's not get into that. We only consider those functions for which the IVP has a unique solution defined over the whole of R corresponding to every initial point. Okay. So now let x be in R. Now let x be a point in Rn for T1 and T2. We can simply verify the following, that if yeah, so we can simply, just a minute, I think I have to slightly, yes, yeah, there's a small change. Yeah. Huh. So consider give for any given x, we denote gamma x to be the unique solution corresponding to the initial point x. So then we consider this, then we define this curve delta, which is all easily seen to be a C1 curve, and then we compute the derivative. After this computation, we see that delta prime t is nothing but f of delta t, and delta 0 is this. So therefore, thus from the uniqueness of the system corresponding to every x, we see that delta x, this delta. So see that this the delta defined here, it satisfies this first condition, and the second condition, just a minute, and the second condition with this. So that means that delta is nothing but the solution of the initial value problem corresponding to this initial value. Okay. So having that in our mind, we define the following map from R cross Rn to Rn, which is defined in this manner. And then it's an easy verification that alpha of T1 plus T2 this is this, and and alpha of 0x is x. So this follows from as I said, the assumption that for corresponding to every initial point x, there is the unique solution of this IVP. So from that it's easy to see that this equals to this and this. So thus alpha defined here is indeed an action of R on Rn. So given an autonomous differential equation, given an autonomous IVP, initial value problem, such that corresponding to every point we do have a unique global solution, then that gives rise to a action of R on Rn. As I said, that actions of R are called flows. So thus we have seen that if we are given such an IVP, then that gives rise to a flow. Okay, so the verifications are quite routine. In fact, so we have just observed that delta is nothing but this, delta is equals to this. So here we put like this, then we apply just the definition. Definition alpha, and this gives us this. Anyway, let's go ahead. Now we will talk about the much more common examples in algebra. So this example is about the action of a group on itself by left multiplication. So it's easy to see that this action is faithful, because no group element G is giving the no non-identity group element G is giving an identity permutation on G if we multiply by that element from the left. And so since this action is faithful, As a consequence of this, one obtains that G is isomorphic to a subgroup of SG. So since G acts on G, so its permutation presentation is this, and since the action is faithful, so there will be a subgroup of SG which is isomorphic to G by this homomorphism. So when G is finite, from what we deduce is known as the Callus Theorem. That is, if G is finite group and G is having, and the order of G is n, then G is isomorphic to a subgroup of Sn. Okay, so this is nothing but a special case of what we have just observed. Okay, and if you remember that already we have obtained S for any and Sn is a isomorphic to a subgroup of GL and C. So if we combine Callus theorem to with what we have obtained earlier, we obtain the following corollary, that every finite group is isomorphic to some subgroup of the general linear group, okay, for some n. Okay, and for this action of G on itself by left multiplication, the permutation presentation associated to that is called the left regular representation of G. Here I would like to make one remark, that it's very tempting to conclude that multiplication, like multiplication from the left, if we instead consider the multiplication from the right, that also gives us an action, but that's not exactly true. You can immediately check that the orders are needed to be flipped. So in order to take care of that, what you can rather do is you can multiply x by G from the right. If you want to multiply x from the right, so instead of G you should rather take G inverse, then it will be of course an action. So this action is called the action of G on itself by right multiplication. So please note that unlike the left multiplication, here when you are considering the action by right multiplication, you have to multiply from the right by the inverse of the corresponding group element, not directly by that group element. Like the left one, you can easily see that the action is faithful. The permutation representation associated to this action is called the right regular representation. So for action by left multiplication, the permutation representation was called left regular representation, and here it is called right regular representation. And how is that defined? It's easy to see that for any G and F, GF is defined as at any point x, it's f of xg. So this is because of that the inverse is already already appearing in the definition of the action. Okay, so the next example we are going to consider is called action of G on itself by conjugation. So how is that action defined? So for any G and X, we consider the conjugation of the X by G. So and then you can check that it's an action of, so this is called the action of G on itself by conjugation. Note that for any G, this the map for any fixed G, the map x goes to Gx G inverse is an automorphism of G. So this observation is very important. The importance you will realize soon, maybe in the next so this in the next few lectures you will see why this is important. So let me again explain that in case of left multiplication, so corresponding to EG, the map was x goes to Gx, or in case of right multiplication it was x goes to Xg inverse. They are just ordinary bijective maps on from G to G, but these maps do not preserve the group structure. These maps do not preserve the group structure of G. But in case of conjugation, indeed this map preserves the group structure of G. So unlike the left or right multiplication, here each group element is giving us an automorphism. So thus a group here is acting on itself by automorphisms. So we will discuss this situation in details later on. Maybe with, as I said, within next few lectures, you will see why this is very important. Anyway, so as the permutation presentation of this action, the permutation presentation is simply is a homomorphism from G to in G. So what is in G? In G is nothing but the subgroup of ort. So so since each, let me again explain. So since each G corresponds to each G, the map that we get is an automorphism of G. So the permutation presentation is actually a map from G to odd G. Okay, that is quite clear. Now to go one step further, we see that like the maps of this form. So the maps Ig for any G, the maps of this form. So these are all automorphisms, right? So the maps of the automorphisms of this form, they form a subgroup of ort G. So these automorphisms Ig are for any G, this automorphism Ig is called inner automorphism by G. So the collection of all inner automorphisms of G that forms a subgroup of ort G. So here we have that the permutation representation is in fact a homomorphism from G to in G. So earlier it was getting into, earlier it was going inside odd G. Now we go one step further and observe that is in fact a map from G to in G. Okay, it's a homomorphism. And what's the kernel of this action? So it's easily seen to be that like if Ig is 1, if Ig is identity, then if Ig is identity, then G must be in the center. That's quite easy to see. So the kernel of this action is the center of the group. Okay, so yeah. Now let's come to the last example, which is in fact the most trivial one. So for any group G and any set X, we can define an action in this way. So equivalently, the permutation presentation corresponding to this action is nothing but the trivial map from G to Sx, and the same goes for the permutation representation as well. So for any group G and any set X, non-empty set, we always have an action of G on X. So this is called the trivial action. You see the reason for calling it trivial, because it's only giving the trivial symmetry, or in terms of homomorphism, we always in terms of the permutation presentation and representation both, we always get the trivial one. So that is why it's quite legitimate to call this action as a trivial action. So thus we have seen many examples of actions of groups. In the next lecture, they are also in the next lecture also we will see a lot of examples. Perhaps those examples will be from much more diverse areas. So I suppose that the entire next lecture will be spent on the discussion of examples only. Then we will go ahead. So with that I will finish this